that back in Chapter 3, Sections 5 and 6. If you have forgotten how to write equations of lines, you could write yourself a little note. Chapter 3, Section 5, and Section 6 will go back over everything on writing equations of lines. You are going to have to write equations of these kinds of lines in Algebra 2. So this is super important. But specifically for this lesson today, you have to be able to write equations of these lines. What kind of line is FG? Vertical. Okay, that's concerning me there for, you guys are too quiet. Vertical. What is the equation of every vertical line? X equals. Vertical, make a note if you did not know that in your notes. Write it down. Vertical lines are X equals a number. It does not fit the pattern Y equals MX plus B or Y minus Y1 equals M times X minus X1. It is not normal. Vertical lines are just X equals a number. So when you look at the line FG, what is the X value that that line is always going to equal? -2. You have a point at -2, 0, -2, 1, -2, 2, -2, -1. So on number 1, your answer should have been X equals -2. That's all there is to it. Okay, what kind of line is EH? Horizontal. What is the equation of every horizontal line? Y equals. And it's Y equals a number. Okay, so what is the Y equals value for line EH? 3. There's a point at 1, 3, 2, 3, 3, 3, but every Y value is 3. Any questions on 1 or 2 now? Okay, numbers 3 and 4 should have been pretty easy algebra. What did you have to do on number 3 first? Distribute the 2. So you should have had 50 minus 2x equals x plus 2. At this point, just depends on what you want to do. I'm going to add 2x. So I get 50 equals 3x plus 2. Subtract 2. 48 equals 3x. Divide by 3. What did you get for x? 16. Questions on number 3? Okay, number 4 is even easier. All you had to do is subtract 3x. What is the answer for number 4? X equals 8. Questions on the 12-1 warm-up? Okay, let's look at the 12-2 warm-up. This is the part that we haven't really talked about this school year. So if you had some trouble with 12-2, it is just the Algebra 1 skills. But this is very important for Section 12-2 notes today. So I'm going to start with, did anybody get an answer for number 1? What'd you get, Devin? 30%. Anybody get a different answer? Okay, what about number 2? 2.64. Did anybody get a different answer? Okay, number 3. 104.4 degrees. Did anybody get a different answer? Okay, all of those are correct, but let's go through and talk about how you did them. So Devin, what did you do on number 1? Were you the one who answered number 1? Okay, what did you do to get 30%? Okay, so you did 18 divided by 60 times 100. Anybody do it a different way and get 30%? Okay, when I read it from the algebra teacher's perspective, I would probably set it up like this. So if you're confused on how Devin knew to do 18 divided by 60 times 100, I would translate the sentence into an algebra equation. What percent? What do we do when we don't know what something is in algebra? X. Of. What does of mean in math? Multiply. So x times 60 is, what does is mean? Equals 18. Then when I look at that problem, if I want to solve for x, that tells me to divide by 60. So that's how we get 18 divided by 60. And then since it said what percent, we have to change our decimal to a percentage. So we get 0.3, and then to change to a percentage, you multiply by 100. Questions on number 1? Okay, number 2, who said 2.64? Elijah, what did you do to get that? .44 times 6? All right, so anybody do it differently? Okay, again, from the algebra teacher's perspective, trying to read a sentence and make it a math equation, I would have said, what number? I don't know what that is, so X is means equals 44% as a decimal is 0.44. Of means multiply times 6. So just translating that sentence, each word into either a variable or a math expression, operation equals multiply, and then solve. So exactly what Elijah did, 0.44 times 6. Questions on number 2? Okay, number 3, Brendan, what did you do? Okay, so it said find the measure of angle WVX. WVX is this part of the circle, which was 29%. 29% is 0.29. And how many degrees are in a full circle? 360, so 0.29 times 360 is 104.4 degrees. Questions on number 3? Okay, so we're going to go through the notes today, 12.1 and 12.2, and I will tell you, it's a lot. And it's just a lot of, like, words. There's not a whole lot to it as far as me really needing to teach you something, as far as it is vocabulary and theorems and just understanding what it's saying. So it can be a little bit boring. I'm just going to warn you. I mean, there's just a lot of information you need to learn today, and a lot of it is just vocabulary and theorems. So we're going to go pretty quickly, and then I'll let you just work some problems and we'll check answers, okay, to try to speed it up and get you talking to your neighbor a little bit. So, like I said, tons of vocabulary. The only thing I want to point out on this part of the notes is just a reminder of how you name a circle. To name a circle, you put a little circle with a dot in it and you name it with its center. So just don't forget how to name a circle. Chapter 12 is all about circles. You cannot tell me what was on the ACT Aspire. I'm not allowed to talk about it. You're not allowed to come to me and say, so Miss Lashley, I had a dream about a problem last night. You can't tell me about the ACT Aspire. But if you had a lot of circles on there, I'm sorry that we hadn't gotten to that part yet. Everything in chapter 12 is about a circle. Okay, so it's just all about circles. First 2 words to me are kind of common sense. When you think of interior of something, what do you think of? Inside. So interior of a circle is just the points inside. Exterior, outside. So the exterior is just the points outside. So some of these words are pretty easy. Chord, secant, tangent, and points of tangency are huge for chapter 12. Tangent here is not really the same as tangent in terms of sine, cosine, tangent, and that's a little confusing. You'll see the connection between this kind of a tangent and tangent when you get to pre-cal, but for now it's just different, okay? Same word, different meaning, so be careful. Chord and secant are almost the same thing, so be really careful with those 2 words. Chord is just a segment, whereas secant is a line. What's the difference between a segment and a line? Okay, say it again, Preston. Okay, segment has 2 distinct endpoints. A line goes on forever. So a chord and a secant are the same thing, except a chord stops and a secant goes on forever. A chord, has its endpoints on the circle. So when you look at the picture, a chord has to go from one point of the circle to another point of the circle. A secant has to have arrows showing that it's going on forever, but it still intersects the circle at 2 points. A tangent can be a line or a segment, but it intersects the circle at exactly 1 point. So do you see that the green line touches at only 1 point? All right. And that point where it touches is going to be called the point of tangency. It's the point where the tangent and the circle intersect. Okay, a couple little things that are going to come back, bless you, to help you or haunt you in chapter 12. Chapter 1 notation. Do you remember all the little picky, make sure you put a line segment, make sure you put arrows, make sure you can name an array, make sure you can name an angle. All those things are going to pop back up in chapter 12. So be careful. If I write this on the board, what is that talking about? Line segment. And in this picture, that is a Chord. If I were to put 2 points here, actually I'll put OD since there's already a C down there. What is this referring to? A line segment. So what would I call that in this picture from O to D? A chord. Be careful, if I do this, it changes it to a line, so it is a secant, okay? How do you name the tangent line? Line M. Remember, you cannot name a line with one letter. To name a line, you have to have 2 points, or you name it with the cursive little letter out to the side, and you have to put the word line in front of it. Okay, so just some chapter 1 notation. Okay, first example I'm going to have you do is this one. Before we do it though, on the homework, the book does not list this. It simply has these directions and a picture. You are going to have to make a note to yourself when you get to the homework and it says identify each line or segment that you may need to look back at your notes to make sure you've listed all of these things. Because they're not going to write them in the book. Do you understand what I'm saying? So when you get to the homework and it has these directions, you're going to need to write on your paper chord, secant, tangent, diameter, radii, and then list all of those things. So go ahead, you and your partner, name every chord, every secant, tangent, diameter, or radius that you see in the picture. And then we'll check it. See how you're doing? Let's go with Hallie, give me a chord. Say it again, I'm sorry. KM. And make sure when you name that chord that you put a segment above it. Are there any other chords? Jackson Quistra. No other chords? There should be one. Very good. JM. JM is also a chord if you put a line segment above it. What else is JM if we don't put a line segment above it? Josh. Secant. Secant. So JM is a secant if you name it with a line above it. So what is every secant going to contain? A chord. And it just depends on what symbol you put up above it as to which one you're naming. So be careful. Every secant contains a chord, but not every chord is a secant. So it depends on if it goes on forever. Are there any other secants in the picture? No. All right, tangent. JP, do you see a tangent? Okay, be careful. To name a tangent line, you can't name it with one letter. So how do we name that line? Line M. Remember that it goes back to chapter 1. You use the little lowercase letter if there's not 2 points on your line. Since there's only 1 point, we can't call it H because we don't know what direction that would make the line. So we write the word line and then we put the little lowercase m. Make sure you put the word line in front. All right, diameter. Ethan, what's the diameter? KM. And notice that KM is in 2 places. Every diameter is also a chord, but is every chord a diameter? No. All right, radius. Give me a radius, David. KL. KL. Give me another one, Sean. LM. And there should be one more, Nicholas. LJ. Any questions on this first example? Yes, sir. It does not. When you name a line or a segment, the order does not make a difference. You can name it either way. All right, moving on. So some more vocabulary here, all about circles. We have congruent circles, concentric circles, and tangent circles. Congruent circles should be pretty easy. 2 circles are congruent if they're the same size. To show they're the same size, they're going to have the same radius length. So as long as they have the same radius length, then they're going to be congruent circles. Some notation to point out so that you don't miss points. Again, to name a circle, you name it with its center. And to say they're congruent, you would use a little congruent symbol. That's something different that we haven't really written a lot. Concentric circles, I think of a dartboard. Concentric circles are circles that have the same center. So they start at the same place and they just get bigger or smaller, like a dartboard. Does that make sense? The thing to be careful about here is if you were to name them, you wouldn't know which one you were talking about, because if you just put circle A, they're all called circle A since they have the same center. So they'd have to give you more identifying information. Tangent circles. What are tangent circles? Exactly. They're two circles that touch at exactly one point, only one point. They can be tangent in two different ways. They can either be internally tangent, meaning that they're inside of each other and touching at one point, or they can be externally tangent, meaning that they're not inside each other, but their exterior parts do touch. Any questions there? Okay. So then we have some more problems we have to answer here on a coordinate plane. I'm going to give you a few minutes to you and your partner to try this on your own first, but I want to point out all the directions here. Be careful. Find the length of each radius. Part B, identify the point of tangent C, and part C, write the equation of the tangent line. Go. See how you do. Okay, I'm not giving you a lot of time, so for some of you, you may not get them all finished, but I want to make sure that we also have enough time to get through all the notes. Again, I want to warn you on the homework. They are not going to do what I did for you in the notes. So in the notes, notice I put circle S, circle R, and then you had a place to write your answer. On your homework, don't just put R equals, and then not identify which one goes with which circle. So you need to identify what your answer goes with. So what is the length of the radius for circle S? About 1.5. Again, notice this is in the center, so you're going to go up 1.5 or down 1.5. What about circle R? 2, so the radius would equal 2. Questions on the first part? Okay. The next thing it asked you to do was identify the point of tangency. Again, on your paper, you're probably going to have to put on your homework something like point of tangency. Don't just write the answer. There's a lot of answers here. So what is it going with? So what is the point of tangency? Where do the circles touch? -2, 0. It's a coordinate. You're on a coordinate plane. Write it as a point. And then lastly, what is the equation of the tangent line? When you look at the picture, first of all, what kind of line would we draw for the tangent line? Horizontal. The tangent line is going in between the two circles, touching here. So what's the equation of that line? Y equals 0. I saw a couple x equals 0s. Be careful, that would have been vertical and that would not be a tangent line. Questions? Okay, moving on again. So some more vocabulary. Common tangent. Common tangent is just a line that two circles both have as a tangent line. So if you look at circles A and B, these red lines are tangent to both of them. So they would be called a common tangent. Tangent lines, if they are a common tangent for two circles, can either be externally tangent or they can be internally tangent. So look at the difference there. What would you say makes a common tangent internally tangent? So what if I hear crossing, but you don't have to have, it doesn't have to be two tangent lines. It could just be one tangent line. So why would this, oops, not really that, that's terrible. Pretend. Why would this line be a common internal tangent for those two circles? It's in between the two circles. So the way the book's going to describe the difference between internally tangent and externally tangent is if you were to connect the two centers. Good grief. If you were to connect the two centers, does that line segment cross the tangent line? No. So if you connect the two centers and it doesn't cross the tangent line, then they're commonly externally tangent. And if they do cross the tangent line, then it's commonly internally tangent. Okay? So a common tangent is just a line that both circles are tangent to, and it's going to be either internally tangent or externally tangent. Questions? All right, here's our first theorem. We are going to learn at least 4, maybe 5 different theorems today. You can just follow along in the notes. You may want to start a list of all your different properties and theorems. It's totally up to you. But this is our first one today, and I'm going to put a list over here on the board as we learn them. Very first theorem. And again, the hard part for Chapter 12 is keeping the theorems straight in your head, memorizing your theorems. You don't need to know what it says in words. You don't need to memorize the name. This is really the same theorem. It just goes both directions, so it's biconditional. Here's what it says. If you have a tangent line, and that tangent line is perpendicular to the radius, it will occur at the point of tangency. So in other words, if you have a circle and you have a tangent line, if you draw a radius to that point of tangency, every single time it's going to create what? It's going to be perpendicular, so it's going to create a right angle. Okay, that's the first theorem. If you have a tangent line, the radius touching the point of tangency will make a right angle. I want to make sure you're clear that it doesn't make a right angle just anywhere. You can't draw a line from here to the tangent line and say that's a right angle. This is not making a right angle. It has to go to the point of tangency, and then it's always going to create a right angle. Okay? What did I just create by drawing that orange line, though? A right triangle, and that's going to come into play quite a bit in Chapter 12 as well. You're going to see a lot of right triangles. Okay? But the big idea here is if you have a radius drawn to the point of tangency, it will always create a right angle. It goes both directions, so that if they show you a picture and it's making a right angle, you can assume that this is a tangent line and this is the radius, because they're making a right angle. Any questions on the first theorem? Okay. Here's the second one for today. Again, I'm going to draw it on the board. And this is what it basically says. If you have a circle, and on that circle you have 2 tangents, and those 2 tangents come from the same external point, then the length of those 2 tangents will be the same. And I didn't really draw this, so it was tangent, so it doesn't really look right. There we go. So the length of those 2 tangents will be the same. The distance from A to B and A to C is the same. Questions on the second rule? Have to come from the same point, and they both have to be tangent to the circle. But if they're both tangent starting from the same point, they're going to be congruent. So try the last example there in your notes with your partner, and then we'll check it. Okay, I'm not giving you a lot of time, but I am seeing the same Chapter 1 mistake as I walk around the room. Be careful. In Chapter 1, for probably first part of the semester, probably the first 2 or 3 months, I was constantly counting off for this mistake. When it says find HG, should my answer be HG equals or HG equals? The first one. This names a line segment. What does the first one do? Tells me the length of the line segment or the distance. You should not have a line segment above it. I don't know how many times I wrote on your papers, no line segment. Don't put a line segment above it if you're giving me its measurement. Okay, what did you do with those 2 expressions? Set them equal because they are 2 tangents. They tell you that. They came from the same exterior point. So set them equal. What did you get for A? 12, and then you plugged it back in to find HG. So you did 2 times 12 plus 4, and you got 28. Anybody not get that and need me to work it? Yes? No? Okay. That's 12-1. Any questions on 12-1? Would you agree it's pretty easy? Would you agree there's a lot of information in it? Okay, here we go, 12-2. Okay, 12-2 is all about arcs and chords, but mainly arcs. Make sure you're with me. 12-2, again, a lot of vocabulary. We're talking about arcs on circles. We're going to talk about different kinds of arcs, and then again, there's going to be a few more theorems we're going to list up here on the board that we're going to learn. First thing is central angle, and I want to warn you, we're going to learn several different kinds of angles. In fact, we're going to learn 4 of them before the end of the chapter. This is only one of the 4. Very important that you understand what a central angle is, or you're going to miss a lot of problems in chapter 12. A central angle is an angle whose vertex is the center of the circle. If you have a circle and you have the center and you have an angle that has its vertex at the center, that's a central angle. Center, central. Everybody good with that? Okay. Arc. An arc is just simply a part of the outside of your circle. So this would be an arc. To name an arc, you're going to name it with either 2 letters or 3 letters, and we're going to talk about when to use 2 and when to use 3, and this is new notation we've never talked about before. So for example, let's say I had endpoints A and B here. To name that arc, I could name it arc AB and put a little arc above it. Just kind of like naming a line segment, but you put an arc. If there's a 3rd letter, it's going to mean something different. So maybe I have a letter here, and I want to name this ADB. What's the difference between arc AB and arc ADB? It's longer. When I have 2 letters, I'm going to go the shortest distance possible. When I have 3 letters, the middle letter is going to tell me the direction to go. So I'm going to go from A in the direction of D all the way to B. So it makes the arc bigger. So when you look at the next slide, you're going to see that there are 3 different kinds of arcs. There's a minor arc, a major arc, and a semicircle. First thing, though, that I want to point out that is not really highlighted or listed great big is this right here. This is huge. You may want to write it down in words on your paper somewhere. The measure of an arc is equal to the measure of the central angle. The measure of an arc is equal to the measure of the central angle. Say it again. The measure of an arc is equal to the measure of its central angle. But be careful, we're going to learn 4 different kinds of angles. So arcs are not always equal to every angle, only the central angle. Okay, so in this picture, if they tell me that angle ABC is x degrees, what's the measure of arc AC? X degrees. The measure of the arc is equal to the measure of the angle. Minor arcs are named with 2 letters. It's not writing very well, but you get the idea. 2 letters. Okay? How many letters do you think we'll use for a major arc? 3 letters. A semicircle can be named with 2 or 3. It doesn't matter. Okay? What do you think a semicircle will be equal to? 180. It is half of a circle, so it's always going to equal 180 degrees. So if they ask you for the measure of a semicircle, it's not going to matter which direction you go. It's going to be 180 either way. What do you think the difference between a minor arc and a major arc is? Major arc is bigger. Bigger than what? Okay, more specific. Bigger than 180. A major arc is bigger than a semicircle. A minor arc is going to be what? Smaller than a semicircle. Okay, so a minor arc is going to be the distance between the endpoints inside the central angle. The major arc is going to be everything outside the central angle. So in other words, if I tell you that this angle is 30 degrees, what's the minor arc? 30 degrees. What's that going to leave then for the major arc? 330 degrees. It's not writing. Are we good? I'm going to say this one more time. When you name an arc, minor arcs are named by 2 letters. Major arcs and semicircles, technically semicircles can be named either way. Major arcs are named by 3 letters. Okay? When you name an arc, you put a little arc above it. If you're telling me it's measure, treat it like an angle. You put a little M in front of it. Notation will catch some of you, especially if you're not paying attention right now. Notation will catch you. So be careful. Measure of the arc equals, or if you're just naming it, you just put AB with an arc above it. All right. See if you can answer this question with you and your partner. I'm going to zoom this back out, so if you're looking at it, sorry. Go back to this one first. If you could please stop and look back up here. First of all, I want to warn you of a couple of things. 1, 3 letters is supposed to be what kind of arc? Major, which should be greater than 180. However, in the book, they could name an arc with 3 letters just so that you know what direction to go, and it might turn out to be less than 180. Don't think you did it wrong. They just named some of the problems with 3 letters so you would know what direction to go. So don't let that stress you out, okay? Check your answers in the back of the book. Come check with me if you're not sure. But if you're naming an arc and it's major, you use 3 letters. If it's minor, you use 2. So KLF means start at K, go in the direction of L, all the way around to F. Start at K, go in the direction of L, stop at F. Okay, so how much of the circle is that? 65%. So back to the bell work. What did we do to find out the angle measure? 0.65 times 360. What do we get? 234. Please look up here and make sure that you understand how to write your answer. Measure of arc, KLF, is the same as the measure of the central angle. So it is also equal to 234 what? Degrees. Arcs are measured in degrees just like angles. Make sure you put your degree symbol. Questions? Okay, second one. They wanted you to find an angle, an arc, and an angle. And you had to be able to pick out what were the sections in the picture. So FMC. Start at F, go to M, and then go to C. We're looking at angle FMC. Angle FMC. So what 3 categories did you have to add together? Pop, country, and R&B. What do those 3 add to be? 30. So you want 30% of the circle, which is how much? 108. Questions on A? Okay, B wanted arc, AHB. Be careful. You're starting at A, going towards H, all the way around to B. You could add all those together, or what's the only thing you're not including? The rock, which is 25%. So how much is left? 75%. So you just want 0.75 of 360, which is what? 270. Okay, last one. EMD, angle. Angle EMD. Go from E to M to D. That's only one section. What section is it? Country. The angle is not 10 degrees. The angle is 10% of the circle. So make sure you did 0.10 times 360, and what did you get? 36 what? Degrees. Any questions? Okay, moving on. So a couple more vocabulary words. Bear with me for a few more minutes. Make sure you understand. Adjacent. What does it mean for two things to be adjacent? Next to each other. So adjacent arcs are going to be two arcs that are next to each other, but they're going to touch at one point. So for them to be adjacent, they have to intersect at exactly one point. They cannot overlap each other. So notice that RS and ST touch at point S. Those are called adjacent arcs. That's going to lead us to our last addition postulate. We had a segment addition postulate, an angle addition postulate. We had an area addition postulate, and now we have an arc addition postulate. And they all basically said the same thing. Part plus part should equal the whole. So if I have two arcs here, the measure of arc AB plus the measure of arc BC should equal the whole arc AC. Okay, part plus part should equal whole. No different than if it's a line segment or arcs. Same idea. All right, so I'm going to give you a couple minutes to try these next couple problems. There should be 2, I believe. Sorry, I'm still in your papers. Yeah, try the next 2 examples in your notes. Okay. Even if you've got the right answers, I need you to listen for just a minute because I'm going to tell you something that's not really on here or needed for here. So if I can have everybody's attention for 1 minute. What kind of angles are these 2 angles here? Vertical, not adjacent. They aren't touching at one common side. They only touch at a point. That's not adjacent. Be careful. They are vertical. What do we know about vertical angles? They're the same. Now here's what I want to warn you about that's going to come up next week and will cost you points if you're not careful. Please look up here right now. This angle is 97.4 degrees, so this angle is 97.4 degrees. Because these angles are central angles, that makes this arc BC 97.4 degrees and this arc AE 97.4 degrees, right? Okay, but next week, we're going to look at pictures like this. Are these 2 angles still vertical? Yes. Are they still congruent? Yes. However, this arc here, AB, is not necessarily the same length as arc CD. And the way I drew it here, they almost look like they are. But look what happens if I draw another. Let me do a different picture. I'll make it a little bit more obvious. Let's do. Okay. Are these 2 angles vertical? Are they equal? Are the angles equal? Okay, guys. I need you to stop giggling. I need you to pay attention. I need you to listen. This is really important, I promise you, for next week. We learned what theorem about vertical angles? It's called the vertical angle theorem. What did we learn about every pair of vertical angles? They're always congruent. So one more time. Are these vertical angles? Are they congruent? Yes. But are these arcs congruent? No. So that's the part I want to warn you about. They're only going to be congruent arcs if they're central angles. If those angles are shifted away from the center, that does not make the arcs congruent anymore. The angles are still congruent, but the arcs are not. So be careful. Okay, that's not really needed for this picture, although you could have found this arc is 97.4 degrees. There was probably an easier way to find the measure of arc BD. First of all, how did you know whether to go BAED or BCD? 2 letters means to go the shortest. So B to D, it should be minor. What did you do to find BD? I know some of you have the right answer on your papers. What did you do? The easiest way, thank you, Jonah, would be to notice that BE is a diameter. Therefore, it's splitting the circle into 2 semicircles. And so what would be the measure of this whole arc all the way around from B to E? 180. And since we don't want the 52 degrees, we could just do 180 minus 52. Does that make sense? And so that leaves us with this angle here is 128. So therefore, this arc is 128. Questions on the first one? Okay, go to the next one. You shouldn't have had this little part here on your notes. Ignore that. Bless you. LJN. What kind of arc should that be? Major. That means you start at L, you go in the direction of J, all the way around to N. So what could you have done to figure that arc out? 360 minus what? 65, because you didn't want 40 and you didn't want 25. So what did you get for your answer? 295 degrees. Make sure you're putting degrees on your answers. Arcs and angles are both measured in degrees. Okay, we have 2 more theorems we're going to write on the board. We're going to go over those, and then I'm going to have you try the last few problems. Okay? So I'm going to skip the examples and go over the theorems first. This one and one more. But first, congruent arcs. This a lot of people miss. Be careful. I'm going to give you 2 pictures up here. That's supposed to be 30 degrees. It's hard to read. Here's my question. Is this blue arc congruent to this blue arc? What's the measure of each blue arc? 30 degrees, right? If this is the center, they're both 30, agreed? But are they congruent? No, because congruent arcs are not just arcs that have the same measure. Congruent arcs are arcs that have the same measure if they are in the same circle or in congruent circles. Are these 2 circles congruent? No. Congruent circles have to have the same radius length. And obviously one circle is bigger than the other. Thank you. Okay? Hi, Jared. So be careful. Even though they have the same measure does not make them congruent. They have to come from the same size circle. All right. 2 theorems left. This one and one more. And I'm going to write them up here on the board. So we really learned 4 rules today, 4 theorems at the end of the day, and a bunch of vocabulary. So here's the 3rd theorem. And it looks kind of crazy up here. All it's showing you here is it can go any direction and it still works. So here's basically what that says on the board, if you'll look over here on the whiteboard. Everybody with me? If you have 2 angles that are both central angles, and that's terrible. Okay, if you have 2 angles, and those 2 angles are congruent, this theorem says not only will the angles be congruent, but the arcs will also be congruent, and not only just the arcs, but also the chords that are formed will be congruent. And it does not matter which direction that you go. So if they tell you the angles are congruent, you're going to know that the arcs and the chords are congruent. If they tell you the chords are congruent, you're going to know that the arcs and the angles are congruent. If they tell you that the arcs are congruent, you're going to know that the chords and the angles are congruent. And that's why they wrote it 3 different times. Because it doesn't matter which one of the topics they give you congruent, the other 2 will also then be congruent. Does that make sense? Oops. Me either. Good timing. Does that make sense? Okay. 4th one, skip a couple examples. So skip all the way to the 4th one. Here's the last theorem of the day. And then it's just examples. You ready? So skip all the way to this theorem. Again, it looks like 2 different theorems. It's the same theorem. It just goes both directions. Look at the board, and I'm going to explain it. So follow up here with me with your eyes. Everybody with me? This theorem says if you have a circle, and in that circle you have a chord, and you have a radius or a diameter or any part of the radius or diameter. If that radius is perpendicular to the chord, then it will bisect the chord and it will bisect the arc. Okay, I'm going to say that again. If you have a radius or a diameter or any part of the radius or diameter and it is perpendicular to a chord, it will bisect the chord and it will bisect the arc. Does that make sense? Okay, I'm going to show you one more thing that may be really helpful for the last example in the notes. I'm not going to work it with you until after you try it on your own, but here is the thing that might be helpful. This is called what again? The radius. What is this? It's also the radius, right? Okay, keep that in mind. And what did I just draw in and create when I drew the radius somewhere else? All right. So it goes both directions though. So if they tell you it's the radius and it's perpendicular, you know it bisects the chord and the arc. If they show you that it's perpendicular and it's bisecting, then it must be the radius, and it means the arc's also going to be split or bisected. Okay, so it can go both directions. Okay, every example that's left in your notes, I'm going to give you 5 minutes to try those, and then we're going to check them. So you only have 5 minutes. Every example that's blank, work it. What does that mean about this arc and this arc? They're congruent. So remember the theorem says if the chords are congruent, then the arcs are congruent. So all you should have done was set those equal to each other and solved for n and then plugged it back in for the measure of arc WS, which means it would have went back into here. And don't forget that arcs are measured in degrees. So your answer for this one should have been, to check your answers, 88 degrees. Okay, if you have a question, I'll come around and go back to it if we have time. The next one, same theorem. If the angles are congruent, then what's it mean about these chords? They're congruent. So you should have set 14t minus 26. Please don't put your stuff away yet. Equals 5t plus 1. If they're equal, you should have solved for t and then plugged that value into nm, which would have went here into 5t plus 1. Here's what I'm noticing though. Be careful. Your answer should have been nm equals 16 with no line segment above it. No line segment. Okay? Everybody good with the first 2? Okay, it's the last 2. I'm only going to work one of them. This one should have been 30, by the way. And then I'll tell you what the last one should have been. Did anybody get the last one? Ooh, I heard 2 different answers, so we're going to check. Okay, quickly, let me show you how you work this problem, though, okay? We still have a couple minutes, so please don't put your stuff away. First of all, this is 8, referring to this distance here. 9 is referring to this distance. So what is the radius? 17, which means if you draw your radius from R to N or R to P, it should be 17, which means you have a right triangle. Be careful though, what theorem over here on the board are we going to have to use after we use Pythagorean theorem here? If this is 17, this is 8, call this x. Which number over there are we going to use? 1, 2, 3, or 4? 4, which says if a radius is perpendicular to a chord, it bisects the chord. So if this radius is perpendicular to this chord, it bisects the chord. If you do Pythagorean theorem here, what are you going to get for x? For x, 15. If x is 15, what is NP? 30. Okay, I heard 2 different answers on the last one, so let's look at it really fast. See where we went wrong. What's this whole distance? 20, which means P to Q is 20. So your Pythagorean theorem should have been 10 squared plus x squared equals 20 squared, which should have left you with x equaling the square root of 300, which is 10 square roots of 3. But that's x. If x is 10 square roots of 3, so is this distance. So what is QR? 20 square roots of 3. And then if you plug that in on your calculator, what is that to the nearest tenth? 34.6? Okay. All right, if you are confused on either one of those, please come in and see me. We have Encore tomorrow. You have your assignment. It's due Monday. See you later.